All right. So to demonstrate the operation and effectiveness of part one of the project, we're just going to move on to part two, which is the IR notch filter design and implementation. Once we implement this on the DSP board, we'll see that the part from section one where we were asked to implement the IR filter program, we'll see that that works. This was cleverly designed in a way so that completing project one would set you up for completing part one of project four would help you with parts two, three, and four. So to start off with the part two, we're going to design and implement a notch filter, which is given by this transfer function, where omega naught is the center reject frequency and omega c is the uh, it's the uh, bandwidth of the reject band, so or of the notch essentially, and it's in discrete angular frequency. So we have to do this conversion over here from to get actual frequency values in terms of hertz. So the first technique we're going to do to derive the z domain transfer function is called the impulse invariance technique, and it basically works by sampling the continuous time version. So we're going to bring the S domain transfer function into the continuous time domain and then sample it, and then bring that discrete time sampled impulse response to the Z domain. So the first thing we do here is just set up the S domain transfer function to a form that can easily be inverse Laplace transformed via the Laplace transform pairs. And we do that by just some algebra. For example, here in the denominator, we go ahead and add and subtract this value so that we can group these components together. And then we add and subtract this value here so that we can get one of these and get one of these here. So you'll see that we're going to treat alpha as equaling omega c over 2. And that allows us to get alphas here, 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 and here. And that way all of these look like Laplace transform pairs. Oh, and same for beta here. In some cases, beta didn't exist in the numerator, and so we divide it out front, like here and here and here and here. And then we just pull out these s's, these extra s's into the front. So then we're just going to inverse Laplace transform each of these parts independently. So the first one has the Laplace transform pair of the exponential times the cosine, and then this s out in front means we have to take the derivative with respect to time of that pair. So we then do that here, and then anywhere we see a t, we substitute it for nts to bring it into the discrete time domain. You'll notice here on the right we have the Dirac delta, and so what that means is since the Dirac delta is only non-zero at t equals 0, we set t equal to 0 for everything that's being multiplied by the Dirac delta, which basically that means that this part just goes to 1. Then when we perform the discrete time substitution, we have to divide by the time interval. So then in part 2, this part right here, we again perform the inverse Laplace transform and then sample to get to discrete time and rinse and repeat for part 3. This part also has a derivative, but in this case, when we have that Dirac delta, this part has a sine instead of a cosine, and when we evaluate sine at t equal to 0, we get 0. And so 0 times the Dirac delta just goes all the way to 0. Then, after getting everything into the discrete time domain, we perform one more substitution in order to get our equations looking like z-transform pairs. So for example, we do the transform here, e to the minus alpha ts is equal to capital E. So for example, this part right here would then be equal to capital E to the n, because the e to the minus alpha ts would all go to e, capital E that is. Then the other substitution is omega equals beta times ts, and this is just to match the z-transform pairs document. And the z-transform pairs, instead of e here, it was like alpha, but we already use alpha somewhere, so we can't do that again, so we use e. And then once we have this, we know transform pairs for this part and this part, and so we do that here. And of course, alpha and beta here are just coefficients, and so they can just sit out in front, or they're just scalars, so they can just sit out in front as coefficients. And then the z-transform of the delta n is just 1, so we just get 1 ts there. And then we just algebra ourselves around until we get this nice transfer function here. Then you have to do that for the other discrete time domain parts, which would be here and here, and then we add them all up, and we get this. And that's how the impulse invariance technique is done. Bilinear transform is a little bit easier. We just substitute every s with 2 times fs times the quantity of 1 minus z inverse plus over 1 plus z inverse. So you see here where we have s's, we now have that that expression. And then a quick and easy technique for cleaning it up is to just multiply the numerator and denominator by some power of the quantity 1 plus z inverse. So in this case, we multiplied the top and bottom by the quantity 1 plus z inverse squared. And you can see it here, for example, and here. Here in the middle, though, we end up losing one of our 1 plus z inverses, and then we end up with 1 minus z inverse times 1 plus z inverse, and that is a factored form of a difference of squares, and so we can just multiply those together to get 1 minus z to the minus 2. And then we have to multiply everything, and then just get to this form where we have essentially everything as a coefficient of some power of z. And there's a trick here with this coefficient in the denominator. Typically we want this to be 1, because right now it's 4 times fs squared plus 2 times omega c times fs plus omega naught squared, and all of those are positive values that are like 1,000-ish, and so they're going to blow up, and this is going to be a huge number, and we're going to have huge coefficients all through our transfer function. So in MATLAB, in order to make this nicer, we go ahead and divide the numerator and denominator by this coefficient right here, so that this becomes 1, and everything else becomes much smaller value. And that's pretty much it. So let's go ahead and go into MATLAB and look at the notch filter. So in this example, or in this implementation, we're setting the format for all the floating point numbers to a long format, which is just the 60-bit format, 64-bit format rather. And then after that, we go ahead and set up all the frequency stuff. So our sampling frequency, for example, the notch frequency, the bandwidth, and then for the purpose of plotting everything, we go ahead and set up some frequency range from negative fs over 2 to fs over 2. Then we move on to generating the filters. And for most of this project, I generate the filters in some external function that passes back the coefficients. So for example, this right here, if we go to this function, here we go. We take f notch and f band and then convert them to the omega naught and omega c, and then perform all those substitutions that we did in the handwritten calculations, such as alpha, beta, e, and omega. And then once we perform those substitutions, we can literally just type in the numerator coefficients and the denominator coefficients as just an array. So there's that fs minus 2 times alpha. we go ahead and look at our theory again, that was right here, fs minus 2 times alpha. So there you go. And then I also had to multiply by this, by the time space here, just to help with the gain scaling. I'm not sure why we need to do this, but it just looks better with that there. In some cases, you don't need to do that, such as with the bilinear transform. It doesn't need you to do that, but the impulse invariance technique seems to. Anyway, yeah, the bilinear transform was right down here. And again, once we perform those two substitutions for omega naught and omega c, we can just literally type in the numerator and denominator coefficients. And like I said before, this part right here, that first coefficient, we then divide everything by that. It's also right here. And so we divide the numerator coefficients by that and the denominator coefficients by that. And that helps bring the numbers down. I'll show that when I do the bilinear transform part. But first, we're going to do the impulse invariance technique real quick. So just for testing purposes, I want to do something that we can actually hear over my crappy audio. So we'll have a notch frequency of 60 and a bandwidth of 20. So let's go ahead and run through everything here. If we go ahead and zoom in, we should see at around -3 dB. At around -3 dB, it should be the notch frequency minus 10 and then the notch frequency plus 10 because we had a bandwidth of 20. And so there we go. Looks good. So I also ran a simulation. The simulation function just works like it does in the Code Composer implementation. It essentially just runs the filter. And if we go ahead and look at the response to a 60 hertz sine wave, we can see that it didn't attenuate at all. It's still 1-to-1 here. Let me show you. Let's see, we set our notch frequency to 600, so let's make the simulation one 600 as well. There we go. And you can see it attenuating, which is what we want. And you'll actually be able to hear this as well whenever we do it for realsies. So let me go ahead and load it up on the, let me load the filter onto the board. Alright, it's running, and I've got a 60 hertz sine wave here, so 60 hertz should pass through. So let's go ahead and listen. Or not listen, but rather let it just play, because I don't have the volume up, but if I turn it up a little bit, you can hear that nice 60 hertz hum. Well, maybe you can, maybe you can't, I'm not entirely sure. There we go. We were getting some harmonics there because I was overloading the ADC on the board. All right, so now we are going to 600 hertz here. My computer's making noises. There we go, that's better. So if I go ahead and I'm just going to mute the 60 hertz and just leave the 600 hertz. So the 600 hertz is playing right now. The moment we can tell is if I just crank up the gain on the 60 hertz above 1 dB, we can see the harmonics come in that come from that clipping. Now the harmonics aren't going to be filtered out because the notch filter is only at 600, and all these harmonics are coming from the ADC being overloaded. And you'll also hear that if I stop and play, you'll hear the boop. That same boop is what's coming from this part right here, that boop. So if we go back. Perfect. It also happens when you when you pause the audio as well, which is funny. Let's go ahead and play some music just to show that the music isn't being affected. I've been thinking so much, I realize I know nothing at all. Your arms set me to see. So there you go. That's the notch filter working for the impulse and variance technique. Now we're going to move on to the bilinear transform technique. So I just switch out these two lines of code here. The notch bilinear function is passing its coefficients to B2 and A2, so that's why I have that there. Something you'll see later is why I decided to use pause this music. It's distracting me. Later on, I'll explain why we have the data type long double here instead of float. And I mean, I'll go in depth with that, but right now I can just say that it helps a lot to have that there. Since in Code Composer, it's using the single precision floating point numbers. By default, it doesn't perform as well, but if you change the coefficients to be double precision floating point numbers, you essentially go from a 32-bit floating point number to a 64-bit floating point number. So it's pretty good. So bilinear transform, I was going to mention, yes, I'm going to show you what happens when we don't divide by that first denominator coefficient. So if I just comment those two out here, and then go ahead and run the code, you can see the filter response actually comes out pretty good. It's here in orange. And it pretty much overlaps with the impulse and variance form. But look at these coefficients, man. They're just way too big. And I'll try and run that on Code Composer just for funsies, but then once that inevitably fails, we'll switch back to we'll uncomment that line, those two lines of code, and have this working. Yep, it broke. Yep, she broke. And I can tell on Code Composer, whenever stuff blows up too big, we end up getting our output buffer filled with nans, which is basically where somehow the floating point number just gets corrupted, either because it blew up to infinity and got multiplied by 0, which can happen, or something else, some unknowable thing. It happens later with the RC filters, and I'll give you my spiel on that when that happens. But for now, let's go ahead and fix this bilinear transform notch filter because it's broken right now. We don't like that. So in order to fix it, do this little division. It's pretty handy dandy. Let's run our code. Oh, and just to be sure we're doing the simulation here, let me go ahead and do that. So there we go. Simulation still shows us doing the attenuation there. You can see, compared to before, we do have a little bit. We do still get some coming through there. If we go ahead and look at the plot here, you see the impulsive variance technique is actually a bit more aggressive in attenuating than the in the bilinear transform. Just barely, by less than like 1 hertz. So yeah, that's interesting. If I go up here, oh. Okay. Oh well, we won't worry about that. Okay, so you see now the coefficients look way better. This is at 1, and so if I go ahead and load that filter onto the DSP board, we should get a working filter. Hooray! Play that beat. And I'll throw in that 600 hertz signal. You heard it. And if you have a good ear, you should still be able to hear it, because this bilinear transform doesn't work as well. If I go ahead and just pause the music, you'll be able to hear it. And there it is. Just tiny little sinusoid, just like we saw in our simulation in MATLAB. So, in conclusion, impulse invariance is superior with respect to the notch filter, or at least just this implementation. And you know, throughout this entire project, I've noticed the impulse invariance technique was way better than the bilinear transform. Of course, the high-pass filter is said to be a bit less robust, a bit more prone to issues, but I did not experience that. I experienced much more issues with the bilinear transform, as you will see. So, with that said, that is it for part 2 of Project 4.